Good morning. My name is Biehler, and I want to give you an update about OPC UAFX. To avoid confusion about the names, OPC UAFLC stands for the initiative, abbreviation for field level communication, and OPC UAFX stands for the name of the specification which is released by the field level communication initiative. And note, FLC or OPC FLC is an integral part of OPC UA. Our specification consists of 5 parts, which are part of the OPC UA base specification. Part 80 will cover overview and concepts, Part 81 connecting devices and information model, 82 networking, 83 offline engineering, and 84 profiles. For our first release, we will cover the controller-to-controller use case. We finalized the release candidate 1 by end of April and are currently working on the release candidate 2. In parallel, the prototyping working group is implementing what was covered in RC1 and what is currently discussed in RC2. By end of August, we will bring the RC2 into a member review, and by end of November we expect to have the version 1.0 ready for release. Later on, beginning in December, we will then continue with the work on the controller-to-device use case. Let's shortly cover the core pieces of OPC UAFX. You may have heard that already in the webinar we gave in last December, or in the podcast, which is also available on the OPC UA Foundation webpage. A central core piece of OPC UAFX is the information model. We are harmonizing access to asset information and access to functional information inside an automation component, which allows then a tool from outside to get a uniform access to information in the automation components, and that is independent of whether the automation component is a device or is a controller, is a drive, a PLC, or a temperature sensor, or belongs to factory or process automation. The asset model describes the world of things, which could be physical things like a module or a connector or a pin, or could also be software firmware licenses. It offers a uniform access to nameplate information, like which vendor the product built, which firmware version it has, serial number, whatever. It allows to assign tags to the asset, and it supports verification whether an asset is compatible to my expectation or not. The asset model is based on OPC UA device integration, part 100 of the OPC UA specification series, and the asset model allows the extension of existing companion specs. The functional model describes the world of functionality, which could be as simple as a digital input or temperature sensor, just offering data, or as complex as a drive. Functional entity supports identity verification. It supports semantics, data types, security, etc. And it supports real-time data exchange. And again, a functional model allows extending existing companion specs, again, PADM or whatever companion specs we have out there. The second core piece, logical connections. Logical connections are serving for the data exchange between functional entities. Logical connections are established by a connection manager. So somebody out here, which could be an external station or could be integrated in one of the automation components, is establishing that data exchange. Establishing logical connection includes the verification of each of the connection endpoints. Are the assets the expected ones? Are the functional entities the expected ones I want to connect? It allows you to get ownership over, for example, the input data or configuration data. It allows you to configure the application behavior of that functional entity, and it allows you to persist connections so that automatically after power cycle the connection is reestablished without the need of someone establishing a connection from outside, like the connection manager. A logical connection is built to exchange data. Currently, we are building the data on top of OPC PubSub, which is covered in the base specification part 14. We allow to exchange normal data and safety data. We allow to secure the data, like to authenticate it or to encrypt it. We support quality of service, like priority up to deadline, including time-sensitive network, including a mapping to time-sensitive networks. Data exchange can be built on various transport, like naked layer 2 PDUs or UDP framing, up to NQ to TNA and QP. And we allow to monitor connections, so that if one of the connection endpoints detects that it doesn't get enough input data, it will stop producing output data or issuing output data. The last core piece is offline engineering. We developed the concept of a descriptor. The descriptor itself describes capabilities, functionality, configuration, and assets of an automation component. In fact, it describes the asset model, it describes the functional model, what we've seen on the previous slides. Offline descriptor is an essential part for development, commissioning, operation, and maintenance phases of an automation system. The descriptor starts by with the vendor making a product. He will fill in some information, and through the various steps of the life cycle of an automation component, the descriptor is enriched with information through the various steps. Like a PLC vendor will offer a product descriptor for its PLC. A machine builder will add functional entities to that PLC and will produce another descriptor or will enrich the product descriptor of a PLC vendor with his information and so on. The descriptor is built on the Open Packaging Convention document, and it allows to package various files, modeling files, including attachment files. It allows to build relationships between the files, and it allows to assign the descriptor to prove the validness of information. Model files will be based on automation MLs, and attachments allow to integrate whatever files you have here. So the Open Packaging Convention document is like a subfile. It allows to, for example, add documents, manuals, drawings, etc. So what I've told up to now is mostly covered in RC1 and the RC1 specification. So what is our current focus for RC2? Actually, it consists of 5 main topics: profiles, safety, security, time-sensitive networks, and we will, last but not least, include feedback from prototyping, which is really valuable to improve our specification. What about profiles? All OPC UAFX devices, or actually automation components, controllers, devices, whatever, will be conformance tested. And profiles define the specific groupings of functionality that will be tested. The crux for a profile, as usual, is on one hand to ensure interoperability in a multi-vendor environment, which tends to a small number of profiles, like one or two or whatever, but still provide vendors with implementation flexibility, which tends to a larger number of profiles. And the real challenge here is to find a balance between these competing goals. And in RC2 profiles, since our first specification will cover the controller-to-controller use case, profiles will be defined for controllers and for the connection manager functionality. As you may already know, OPC UA Safety Part 15 defines safety communication. The Safety Working Group is currently in the process extending their, up to now based on client-server communication, extending it with a mapping to PubSub based on Part 14 of the base specification. This extension, or actually the complete OPC UA safety communication standard, is currently in member review. Safety works in a way that the safety consumer is communicating with a safety provider. Safety provider would, for example, be an emergency stop button or a light curtain or some safety component. The safety consumer issues a request SPDU to the safety provider containing protocol information, which requests the safety provider to provide a new set of safety data to the safety consumer, which is included in the response SPDU. Response SPDU contains safety data plus protocol data. In the information model, the safety provider is modeled inside the safety information model, having parameters and the PDUs, which we have seen here up there. The request PDU and the response PDU. If we now combine safety with FX, means safety variables, speaking the request SPDU and the response SPDU, are also organized by the input data and the output data of the functional entity. So both safety provider and functional entity input data point to the same instance of a base data variable. Meaning, functional entity may now specify safety and non-safety variables in parallel, and connections, which we have seen on a slide before, may exchange safety and non-safety data in parallel. We may even include multiple safety providers or consumers at one time. Security, the next extension or the next topic in our RC2 progress of the specification. Security is what we do as FX. We will use the security features provided with the OPC UA base specification, meaning authorization, authentication, and encryption. And with actually 3 areas where we will apply security features. One area is client-server communication. Client-server communication will be used for accessing data in the information model. Plain OPC UA base communication or base security. And we will use role-based security, especially for example for the connection manager when he will establish the connections. The connection manager will use normal client-server communication to establish connections, but the connection manager is a service. It's not a human person. So what we need as extension is new non-human roles which we have to define. Regarding PubSub, we will base our security model, or we will base it purely on what is specified in part 14 in the PubSub base communication specification. And we will support the pull and the push model, which is defined there. Take a look at the concept section of part 14. PubSub will use symmetric keys for real-time purposes to avoid a long time for encryption or decryption. However, if you use a symmetric key too often, you have to renew it. And for the renewing of the symmetric keys, you need a security key server, or abbreviated as SKS. We will profile it in a way that the connection manager will also act, or actually the device where the connection manager is sitting on as a service will act in addition as a security key server as defined by part 14. And last but not least, the offline descriptor, as we've seen above, will use also security features like signing or encryption. Last but not least, for RC2 time-sensitive networks, abbreviated as TSN. TSN depends on outcome in various IEEE working groups, which will unfortunately not be available in our release timeframe. For example, the outcome of the 6002 profile working group, which defines an automation profile over TSN, or various young modules are not defined. Wherefore, we defined 3 meaningful steps towards full support of TSN in OPC UAFX. The first one is network-only TSN, which will provide with RC2. The second one is offline engineered static TSN, meaning offline engineered streams. And the last one is plug-in produce TSN, meaning online engineered streams. Both will be covered in future releases. For network-only TSN, an end station component may still use its traditional Ethernet interface, but has to add the priority tagging of Ethernet priority, meaning PCP, or IP priority, meaning DSCP, when injecting the frames. The bridge components are set up with a 6802 aligned TSN bridge capability definition, meaning the bridge components are set up using time-aware shaper windows and or preemption. And for the network services, we expect to be either RSTP or MSTP there. We need still to decide that. We expect to have LLDP and 802AS for working clock synchronization to establish the time-aware shaper windows within the TSN domain. That's it for my presentation. Thank you for your attendance. If you have any questions, don't hesitate to contact me. Here is my email address and my telephone number. If you look for more information, navigate to opcfoundation.org/FLC to get white papers and brochures. And also go into the concept sections of the FLC specification series to get more information.